So let us look at the usual set of examples. Plane. What is the normal vector field? Normal is a constant, right? Same vector at all points. I'll forget the point P, okay? So this is with the earlier notation ABC, right? 1 over so in this case the function is a constant function. At every point it is the same. So n is a constant, namely this. So you just get the same point on the sphere for every point in the plane. Same normal vector at every point. So what happens to the sphere? So this is right. So n is what? Norm of this square root of 4x1 square blah blah blah. So 2, so this will 2 cancel off. We will again just get right. That is the identity function, identity map, right? Your surface itself is a sphere. Gauss map is into the sphere, so it's the identity map on the sphere. So identity. Look at the hyperboloid, or what was that? Look at anyway, it doesn't matter. So hyperbolic paraboloid, okay. Minus 2, 2, minus 2x, 2y, 1. At any point x, y, z. So normalize it. there's some point. So these are all points on the sphere S2, right? Do you get the whole of S2 as the image? In this case, or is there some point on the sphere which is not in the image here, the range of n? So forget this normalizing factor. You have last factor is always 1 here, right? So you take any point whose last coordinate is not 1. I mean, not 1, but positive. So this is always positive. This is a normalizing factor here. So something positive, 1 over something here. So for example, E1, 100 is not in the image. Same thing about E2 also, right? Of course, E3 is there. You can take 001. So you'll get. So E1, E2 are not in the image, for example, right? Can you tell me what exactly the image is? All points of this form, x and y, are arbitrary real numbers. So what is the set of all such points? So these points are not there, already we have mentioned. Is there any point on this equator in the image? We have just said E1, E2, or plus or minus E1, E2, E1, you can say they're not in. Some point here, for example, is that in the image? None of the points on the equator lie in the image. What about points below the equator? Z coordinate is negative, right? So Z here is strictly greater than 0. So Z less than or equal to 0 points are not there. That means the lower hemisphere is not part of the image. What about the upper hemisphere? The whole of the upper hemisphere is open, of course, right? And closed on the curvature. 0 is also excluded. So this is equal to the open upper hemisphere. Look at the case of, so look at the 3 cases that we have seen, okay? Plane, of course, the image is just 1 point. It's a constant vector field in that case. The case of the sphere is the identity map. So what is the image there? The whole thing, whole sphere, right? This is the identity map. So every point is in the image. So the first and the third examples here, the image is not the whole sphere. Whereas the second, it is the whole sphere. Do you see any reason why this should happen, nature of the surface. So the first case you had the plane. The third case you have the hyperbolic paraboloid, right, which is again a unbounded thing, right? Whereas the ball, the sphere here is a compact surface. Plane and the hyperbolic paraboloid are non-compact. So the reason is precisely this. There is a theorem which says that if you have a compact, connected, oriented surface, the Gauss map is surjective. F S is compact. Because all other assumptions we already made in general, right? Oriented, connected, and so on. S is compact, then the Gauss map is onto. The image is the whole of the sphere. Okay. The image of the Gauss map. Of course, this injective and surjective terms, these are the Bourbaki terms. They come from French. Sur is on. We usually say surjective, but some people, Raghunathan, for example, says surjective. Sur, the French word is sur. Sur is on, so surjective is onto. Oh, okay, we can look at the picture there, for example. So we had the hyperbolic paraboloid. So here it is elliptic paraboloid. So this is the surface. So this is the corresponding picture on the sphere, right? So you have, see, the regions are appropriately shaded there. So points here map to these points here by the Gauss map and so on. Okay. Elliptic paraboloid, how do you write the equation? Instead of minus, you write plus, right? Of course, you can put coefficients if you want. X square by a square minus y square by b square, and so on. It's just a rectangular hyperbola that you get, right? So the elliptic paraboloid is like this. Is that compact or non-compact? It's of course closed, right? Always closed. But is bounded or unbounded? Unbounded. X and y are arbitrary, so Z also is arbitrary, large. So is non-compact surfaces, right? So you don't have too many compact surfaces, right? You have the sphere, you have the torus. Essentially, that's all. There's a theorem which characterizes the characterization theorem for compact orientable surfaces. So you can describe all the compact surfaces in terms of the sphere and the torus. For example, what you can do is you can put them together. So this is a sphere. You have the torus here. So what you can do, for example, is join them together. So remove a small circular portion from here, remove a small circular portion from here, and glue them together. So you will get something like this. I'll draw the picture this way. Or picture இப்படி போட்டா you don't get a feeling of what is going on. So let us put the thing over top. So this is figure irukanga illa, I don't think, because I mean this is just off the track. So this is the surface which is got by attaching a handle to the sphere. So this is like a handle, right? இப்போ பூட்டு மாதிரி இருக்கு பார்த்தா, right? So this is again a compact orientable surface. Of course, you can put more handles if you want, attach more handles. So one topologically, what is the difference between this and this? Both are compact, but the other one has a hole, so to say. So this is simply connected, whereas this is not simply connected. Okay. As you attach more and more handles to the sphere, you get surfaces which are less and less simply connected, so to say, right? Multiply connected, more and more multiply connected, you can say. The fundamental group in this case is going to be Z cross Z, so we'll have more copies of Z there. So, but the number of handles that you attach is a topological invariant, which means that if you have a sphere with m handles and a sphere with n handles, they are homeomorphic if and only if the number of handles here is the same as number of handles here. So the number of handles is a topological invariant. It's called the genus of the surface, which in turn is related to the Euler characteristic that I had mentioned earlier in context of Gauss-Bonnet theorem, right? The Euler characteristic is 2 minus 2g, where g is the genus of the surface. So all these are topological blah blahs. Okay. So just to say that there are many compact orientable surfaces, but you know all of them. There are not too many of them. There are infinitely many, but there are not too many of them. When we computed tangent spaces, look at the cylinder, our usual circular cylinder. So going back a little now, I wanted to point out something there. Okay. So if you take a point on the cylinder, so what is going to be the tangent plane? Okay, now let's write it down and see. Okay, so what is the sphere cylinder is x square plus y square equal to 1. The gradient is 2x comma 2y. So no, tangent space. No. So okay, so 2x 2y 0. What is the orthogonal complement of this? For a point on the sphere, on the cylinder. Let's take some fixed point if you want. So 1, 0, 0, let's say, E1. Is going to be 2, 0, 0, right? So is the YZ plane. So this is the point 1, 0, 0. Okay. What are the points of contact of this YZ plane and the cylinder? So the plane is going to touch the cylinder along a line, along a generator, so to say, these vertical lines. So in other words, the tangent plane geometrically, so whether you take a point here or a point here, so all those points, the plane is the same, right? Irrespective of the z coordinate. The tangent plane here is a plane like that. Tangent plane here is also the same plane. So all points along the generating line there, you have the same tangent plane. Okay? So this is something I wanted to mention, I suppose. I think you had a picture for another surface also of this kind, this image of the Gauss map. So now we come to the most important part of this. So you have the Gauss map, which is a smooth map. So you can talk of the derivative of the Gauss map. So what is it? Before that, maybe I'll say a few things about. See, there are here what are called the classical terminology. This is again the fundamental forms associated with the surface. What is called the first fundamental form and the second fundamental form. So what is a form here? Form here just means a quadratic form. So what is meant by a quadratic form? Classically, of course, it's in terms of square of something, square of something, plus. But what is it? So you have what is called what are called bilinear forms, right? Okay, so you have inner products, first of all, for example, right? And you have the norm given by the inner product. Norm square is inner product of something with itself. So inner product is a bilinear form, right? The norm square is a quadratic form, right? So what is a bilinear form? Generally on a vector space, let's say, okay, all real for us. You have a real vector space. You have a scalar valued whatever from V cross V to R, which is linear in each coordinate, right? Linear in U, linear in V. So linear in each variable there, then you call it bilinear. Of course, you can have more than two, trilinear, in general, multilinear. Okay. So this is a bilinear form. So it's a form always refers to scalar valued maps. Okay. So bilinear scalar valued map. That's all this means. So if you take V is equal to U in this, phi of UU. So this is a function of just one variable, V to R. Right? So this is what is called a quadratic form. Of course, later on we have to talk of some other forms. There, just form will mean something else, some differential forms. So here, when you talk of the fundamental forms of a surface, they are quadratic forms. So an inner product is an example of a bilinear form, and the norm square that you get from the inner product is an example of a corresponding quadratic form. So in general, of course, you can take any linear map, for example, A V to V, linear, and you can compose with, you can take even two linear maps if you want, and put a here, B here. You will still get a bilinear form. Of course, when you want to look at the corresponding quadratic form, you take V equal to V. But the thing which is of interest to us is just when you have a single linear map like this, and look at the corresponding inner product. AU dot V. We either write dot or put the bracket like this. This arrow bracket for inner products. The usual Euclidean inner product, AU dot V. So this is an example of a bilinear form, and the corresponding quadratic form is like this. Of course, when A is the identity map, you get the earlier one. It doesn't matter. Of course, the inner product is a special kind of bilinear form, right? It is positive and positive definite and so on. In general, bilinear is just bilinear. No, you don't. It doesn't have to be positive or definite or anything. So when you look at a surface and look at the tangent spaces to the surface, so these are all subspaces in your ambient space, Rn plus 1. By the way, I have been using this word, I don't know whether familiar with this. I think even from the first class I have been using this. Ambient space. Are you familiar with this word? Space around, let's say, right? You generally also talk of ambience, right? The general. How is the general ambience in the class? You probably say ambience, right? I'm saying ambience because it's French. So the ambient space is surrounding space. You have a surface sitting inside a Euclidean space, so that Euclidean space is the ambient space for the surface that you are looking at. Okay, so our surfaces that we are looking at are not abstract surfaces. They are all sitting inside some Euclidean space. So that Euclidean space is the ambient space for the surfaces. So Euclidean spaces have the natural inner products, right? And so this inner product on the ambient space induces inner products on all the tangent subspaces. Tangent spaces are just subspaces of the Euclidean space. So if you have an inner product on a vector space, all subspaces inherit the inner product from the bigger space. So all tangent spaces to the surface are already endowed with an inner product which comes from the inner product of the ambient space. So in our setting, therefore, the inner product that you get on the tangent spaces to the surface from the inner product in the Euclidean space where the surface is sitting. So this is what is called the first fundamental form. And this is a classical terminology, so of the surface. What is this? This is just the quadratic form inherited by the tangent spaces from the Euclidean space, ambient space. Tangent spaces, which are all subspaces of the Euclidean space. Okay, so this is already there, so we don't have to do anything about it. So now we come to what is called a second fundamental form, that is going to be of this type, coming from some linear map on the tangent spaces. So that linear map is what we are going to look at. Okay, so that is basically the derivative of the Gauss map. This linear map is going to be all important because of the fact that this linear map, or the corresponding form if you want, is going to measure, in some sense, the rate at which the surface turns, or the normal to the surface turns at a given point. Normal is the orthogonal complement of the tangent space, so you can also say the way the tangent space turns at a given point. So this measure of turning of the surface is going to give you what is called curvature. Huh? Not 10, of course. En. This way of expressing or getting curvature came later. The way Gauss looked at curvature was different. So you look at the Gauss map, take a point, take a small neighborhood of the point, look at its image on the sphere. Okay? So take a point here, take a small neighborhood there, take a corresponding image there, look at the area of this and the area of that, look at the ratio of the areas, and see what happens as your neighborhoods shrink. Right? Neighborhood of P shrinks to P here. Similarly, the corresponding thing happens there. So the areas, both the areas shrink to 0, but the ratio has some fixed limit, which may be 0, may not be 0, may be positive, may be negative, anything. Right? So this ratio is what Gauss called as the curvature. So now, of course, we define it differently in terms of linear maps and so on, but now that becomes a theorem. What was Gauss' definition of curvature? That becomes a theorem. That the curvature that we are going to define using the Weingarten map is the ratio of the areas as the neighborhoods shrink to 0. Okay? Of course, we will not be proving that theorem or even probably stating the theorem, because it involves, first of all, you have to specify what you mean by area on a surface, right? Area of a patch on the surface. So you can do that, but we are not going to do that. So first of all, you have to define the areas, what is meant by surface areas, and then that becomes a theorem. So we are not going to touch that at all. So take a surface, okay, with all the usual attachments, right? F is a function from U to Rn, etc., u to R, and so on and so forth, smooth. with non-zero gradient, all those things. Sorry, F inverse. See, P is a point on the surface, and B is a tangent vector at P. So this means what? V is going to be, you have a parameterized surface, alpha prime 0 or something, okay? For a suitable, where alpha is a parameterized curve passing through P, and the derivative velocity vector is tangent vector, the usual setting. Now we are going to define a new kind of derivative. So this can be done for all vector fields, but we are going to look at it only for the orientation vector field, normalized normal vector field, unit normal vector field, that is. Look at n of alpha t. Look at the derivative at 0, right? D by dt, n composed with alpha. So this is the what is called the covariant derivatives, but we are not going to use any such terms here. So, okay. Going to define W of or LP, if you think your book uses LP, of V by definition is I have to put some arrows somewhere, so on. So if you want to talk of tangent vectors, you usually put arrows there, okay? So where does this object lie? LP is LP of V. What is this equal to? Chain rule. So in general, what is your X? If X is a vector field, so what is it? The derivative of what? So maybe that's a good point to stop, right? Just see what object is that. So one would like to ask, what kind of animal is there on the right hand side? Is it a tangent vector again, or what is it? What does the chain rule give you? N dash, what is meant by N dash? You mean Dn? Huh? Hmm? Dot product of alpha dash or alpha dot or whatever. So what is it? What is the object on the right hand side? So what the map? What is your LP then? What does it do? Okay, so we'll continue. Think about this and come back tomorrow. We'll start with this again.